Hey everyone and welcome. Today we are climbing the ladder of artificial intelligence. We're going to break down how intelligent systems get built, starting from the absolute basics, simple reflexes, and going all the way up to machines that can actually learn. So let's jump right in.
But before we can even start building an intelligent machine, we kind of have to wrestle with a much older question.
I mean, that's the big one, right? Can a machine think? This is the huge philosophical puzzle that really kicked off this entire field. And to make it something we could actually work with, the pioneer Alan Turing came up with a brilliant pivot. He said, look, instead of asking if a machine thinks, let's ask a different question. Can it act so much like a thinking human that we can't tell the difference?
And that idea brings us to the famous Turing test, which he proposed way back in 1950. The real genius here is that the test doesn't care about the code or the circuits or what's happening inside the machine. It's all about performance. It's a hands-on test that just asks one simple thing. Can this machine hold a conversation just like a person?
The setup for this is actually beautifully simple. You've got a human judge, the interrogator, who's basically just texting with two other players that they can't see. Now, one of those players is another person, and the other one is the machine. The judge's only job is to chat with them and figure out which is which. And here's the key. Passing the test has nothing to do with proving consciousness or, real understanding. It is all about successful imitation. If that machine's conversation is so believable, so human-like, that the judge is fooled, it passes. It is, for all intents and purposes, acting humanly. Okay, so the Turing test is a fascinating benchmark, a really great thought experiment. But in the real world, AI researchers today, well, they approach the problem a little differently. They focus on building something they call a rational agent.
This right here is our fundamental building block. An agent is just anything that senses its world and then acts on it. Seriously, that's it. A thermostat is an agent. It senses the room's temperature and acts by turning on the furnace. You and I are agents. We sense with our eyes and ears and act with our hands and voices. Even a software bot is an agent. They're everywhere.
And every single one of these agents, no matter how simple or complex, runs on this exact same loop, over and over again. It perceives the world, it thinks about what to do, and then it acts. This cycle is basically the heartbeat of all artificial intelligence.
So to design one of these agents, we need to clearly define its job. And for that, we use the PEAS framework. Let's use an automated taxi for an example. The P is for performance. What makes a good trip? Well, it should be safe, fast, legal, and comfortable. The E is its environment, the messy, unpredictable world of roads, traffic, and people. A is for actuators, the parts it uses to act, like the steering wheel, accelerator, and brakes. And finally, S is for sensors, how it perceives the world, using things like cameras, sonar, and its speedometer. This framework lays out the entire problem the agent has to solve.
All right, we've got our foundation. We know what an agent is. Now, let's actually build one. We're going to climb this ladder of intelligence, starting right at the very bottom rung.
And at level 1, we have the simple reflex agent. This is as basic as it gets. It works on simple if-then rules. If the brake lights on the car ahead turn on, then I hit the brakes. It has zero memory. It's pure reaction, based only on what it sees in that exact instant.
But you can probably see the big limitation here, right? This only works if the agent can see everything it needs to make the right decision, what we call a fully observable environment. But what about the car that just went into its blind spot? To handle a world that's only partially observable, our agent needs a serious upgrade. And that upgrade is memory. The solution is to give the agent an internal state, basically a model of the world that it keeps in its head. This lets it track things it can't see right now. It can remember, hey, there was a car behind me a second ago, even if it's currently in a blind spot. And trust me, that is a huge leap in capability. So our agent is getting smarter. It can react, and it can remember. But that's still not quite enough. It's still just kind of drifting, right? It doesn't have any purpose. To get truly intelligent behavior, we need to give it some ambition.
The next step up the ladder is to give the agent a goal. Now, instead of just reacting to the world, it can start to think ahead. It can ask itself, okay, what series of actions will get me from here to my destination? This is what allows for real planning and finding a path to a good outcome.
But this creates a new, much more interesting problem. Having a goal is great, but it doesn't tell you the best way to get there. Is the fastest route always the best one? What if it's full of traffic? What about the safest route or the most fuel efficient?
And this brings us to our next level, the utility-based agent. This agent doesn't just have a goal, it has preferences. It uses what's called a utility function to figure out how happy a particular outcome would make it. So route A might be way faster, but if the agent's utility function values safety and saving money more than speed, it will rationally choose the slower route B. It's making an optimal trade-off based on its priorities.
So we've built an agent that can perceive, it can remember, it can plan, and it can make optimal choices based on its preferences. There is only one rung left on our ladder. This is the top. The agent that can get better all by itself.
A learning agent has 4 key parts working together. First, you have the performance element. That's the agent we've already built. It's the part that actually does things. Then there's the critic, which is like a coach watching from the sidelines. It gives feedback, saying, hey, that was a good move, or oof, that was a mistake. The learning element takes that feedback and actually changes the agent's rules to do better next time. And finally, the problem generator is what pushes the agent to explore and try new, sometimes weird, things, which gives it new experiences to learn from.
And you might be thinking, this is all just theory, right? Nope, this is in millions of homes right now. The iRobot Roomba is a perfect example of this whole ladder in action. It senses dirt, it builds a model of the room, it has a clear goal, get the floor clean, and newer models actually learn and become more efficient over time. It's the entire ladder of AI cleaning your floors.
So we've climbed the ladder. We've gone from a simple twitchy reflex all the way up to a sophisticated learning machine. We have the blueprint. The engineering, believe it or not, isn't the biggest challenge anymore. The real question, the one we all have to think about now, is a question of values. As these agents become more powerful, what goals, what preferences, what lessons should we be teaching them? That's the question that's going to define our future.